Thank you, Jacob. My name is Steve Beck. I'm an assistant professor at the College of Engineering at the University of Iowa. Today, I'd like to talk about our new project called Driver360. This is a project that's funded by the SaferSim, and we've been doing some interesting stuff for integrating camera imaging technology into the driving simulator. Before to get into the details, let me talk a little bit about the background. My group is primarily interested in analyzing different shapes. Body shape could be, one good example. So, obviously, a lot of people have all different body shape. Our goal over here is somehow mathematically characterize and parameterize their body shape using some variables. So one naive idea would be to take 3D scans, and then using the 3D scan data, we can quantify the XYZ coordinate values of different body parts. And then if we somehow do it in a systematic manner, we can actually achieve a pretty dense discretization of the 3D body shapes. That basically give us a sort of a vector representation of the body shapes. And those vectors are basically a numerical characterization of how people look like. Now, these vectors are basically mathematical quantities, so we can map that into some high dimensional space. And then within that high dimensional space, not only those three, but also there are lots of other scan data. So by doing some statistical analysis, we can derive a mathematical equation um, that basically represents the distribution of how people's body shape look like. Now, further, we can parameterize the body shape space using a handful number of parameters to make our lives more easier. So after doing that sort of parameterization, what we can do is to control the body shape by changing those modeling parameters. So by tuning those knobs, we can basically create a lot of different body shapes from that statistical distribution. And what that means is the 3D model that's created from that statistical model will be highly realistic because we're basically relying on the actual 3D scan data as opposed to model the body parts using some simplified mathematical model. So this is our previous work on South Korean body shape. So we analyzed 250 body shape, 3D whole body scan data of South Korean residents, and then we statistically analyzed those body shapes, and then we extracted some body parameters. So as you can see on the left top corner, there are some parameters, some slider bars that we can tune, and then by moving those slider bars, we can in real time create a 3D realistic body shape model. Now, to expand this research, we've been investing our time and efforts in creating this camera imaging studio, which is comprised of 100 DSLR cameras that are all connected and centrally controlled by a computer. What we can do using this system is we can record videos, we can take photographs from different directions. And then we have this technology called photogrammetry, which is combining the multi-perspective images. And then by using those visual information from different directions, we can create a 3D model out of it. So it's basically like a fast speed 3D scanner that can scan things in 60 frames per second. So what you're seeing on the right-hand side are some examples of what we can produce from that system. And as you can see, it's basically like a 3D scan. of different people doing different things. So the idea in this Driver360 project was to integrate this into the driving simulator. So the idea is to install some cameras inside of driving simulator, and then we record videos and images of drivers of the participants from that setup. And then using this 3D reconstruction algorithm, the goal was to reconstruct a 3D model that has a very high resolution 3D geometric data of the research participants. So particularly the objective of this Driver360 project was to build a hardware setup to collect video data of vehicle drivers in our MiniSim driving simulator. And then more particularly, we use this project to build this a camera rig that can be added to an existing MiniSim configuration, so that without dismantling anything in the existing MiniSim simulator, we can actually add these camera devices on top of the existing mini-simulator. Also, having this multiple cameras, having this large number of cameras, require us to be able to control all of those cameras somehow in an intelligent manner, instead of visit all the cameras individually and then pull the trigger. Instead, what we'd like to do is to somehow hook up the cameras and then connect all of them to a trigger, a single trigger, which fires all of them up with a single click. So that's the second objective. And then the other objective was to, another issue with this kind of camera system is the power supply. So obviously the DSLR cameras, basically they work with batteries, but it's not desirable to charge batteries all the time and then replace the batteries all the time. Instead, what we'd like to have is a centralized power supply system that can be plugged into a typical wall outlet and then distribute the power to individual cameras. And then lastly, we wanted to have a protocol for video data transfer from camera to a computer, such that without having to worry about pulling off the SD cards and then copying all the images, we would like to have a software system that automatically download the videos from cameras to a computer, so that the images and videos can be processed afterwards. The reason why we want to do this is basically there are two different reasons. One is to create realistic driver avatars for simulation. So this is an example of one of the projects that we're working on outside of this Safer Sim project. So right now the US DOT, the Federal Highway Administration, is sponsoring us for developing technologies for connected simulators. So the University of Iowa, we have the National Advanced Driving Simulator. And then on the main campus, we also have pedestrian simulators and bicycle simulators. And then the goal over here is to connect those simulators that are located in physical different locations into the same virtual world, such that the participants can actually interact with each other in a virtual space. And to do that, one of the critical technology is to create a person-tailored avatar for those research participants. So ideally, what we would like to have is some sort of avatar generator sitting inside of the graphics engine. And then whenever there's a research subject, we can briefly measure their body sizes. And then that information goes into the avatar generator. And then the avatar generator generates an avatar based off of the body measurement provided as an input. Another way to think about the avatar is actually the physical simulation. So not the driving simulation, but we can also think about a situation where there's a computerized character inside of a CAD system. And then when the designers design a vehicle or other machinery, having an accurate anthropometric model inside of the CAD system is actually very important. So our hope is by having this rich data set of 3D scans of drivers, we should be able to provide more, accurate anthropometrical reference for the people who's designing vehicles. The second motivation is slightly different from the conventional use of avatars, which is uh, so a lot of people these days are talking about computer vision and deep learning systems, and then those deep learning algorithms basically require a lot of image information to train them. So with deep learning, for example, what we can do is to develop an in-vehicle monitoring system that monitors people, that records the videos of the people in the car, and then we can, track their kinematic motion, their facial expressions, and a lot of things can be measured through optical sensors. But the problem is, in order to train these kind of algorithms, you actually need to have a large number of images that are all somehow annotated. So what that means is you got to have the ground truth locations of the eyes, nose, lips, neck, shoulders, and all these body joints needs to be somehow annotated. Okay, so having just merely an image doesn't really help for training those deep learning algorithms. You actually need to have those body landmarks somehow annotated by somebody. So the idea here is when we train those deep learning algorithms, we could probably train the algorithm using some synthetic images instead of the images of real people. So the idea is if we have a large collection, a large library of 3D driver models, we can then generate some fake images of drivers in a lot of different situations. We can put the driver inside a truck. We can put the driver inside of Tesla. We can put the driver inside of Toyota. We can control the illumination. We can control the direction of light. We can make it darker. We can make it brighter. In the virtual graphical rendering, we actually have a large we have so many control over the scene that we can generate. And then the benefit is when we graphically generate a scene, then we can actually trace back which of which pixel comes from which object in 3D scene, and then by tracing that back, we can have a very accurate labels for each individual pixels, which basically says this pixel over here is an elbow, this pixel over here is the wrist, and so on and so forth, so that without having to deal with this tedious process of image annotation, we can actually populate an image database for the training of deep learning models. Now, in this particular project, we focused on the construction of the hardware setup for facilitating image acquisition for us. So the first thing we did was to draw some CAD. So we roughly modeled the dimensions of the existing mini simulator. And then on top of that measurement, we designed this rig that is portable so that we can move to different locations, and then can be added on top of the existing driving simulator setup. Now, using this hardware structure, then the other challenge was to connect the cameras and then supply the power to those cameras. And then for these, in our previous version of that full-scale 100-camera dome, we actually, fabricated everything in-house. And then from that experience, we actually learned that it's really difficult to make things really stable and robust. So this time, instead of making everything in-house, we actually work with a company in the United Kingdom called Asper. They are specializing in this kind of multi-camera setup and multi-camera control and tethering of the cameras and things like that. So they have quite substantial know-hows and experience in terms of how to connect the cameras and how to make this multi-camera system work robustly. So one of the solutions that they provided was this battery pack. So what you see on the picture, you can see a battery pack with a wire, and then in the meantime, you can see a battery pack without a wire. So the one without a wire is the original camera battery that comes with the cameras. And then what the one with the wire is actually the dummy battery. That's not really battery, but it's somehow connected to the wall outlet. So there's a DC converter circuit inside of this power box, and then the AC current coming from the wall outlet is converted to DC, and then those are distributed to those dummy batteries, and then the camera is supplied with power through those dummy batteries. Another thing that we did was, so we worked with Asper again, and we we made this trigger boxes. So the role of the trigger boxes is to deliver the shutter signal. So all of the cameras actually come with this port for remote controller, so wired remote controller. So the professional photographers use that remote controllers to, control the cameras from remotely. And then what we can do is to somehow daisy chain all those remote controllers, remote control ports of the cameras, and then we can have a circuit that distribute the shutter signal from one camera to all the others. So Asper did a brilliant job in making that circuit and then making everything work robustly. So in our previous project, the in-house trigger box that we developed, the latency of the signal delivery, the synchronization, was around 50 milliseconds. And then Asper, actually, they deliver a solution with like 10 millisecond range of latency, which is way faster actually than the actual response time of the camera, so that it's very robust, and the synchronization quality is very satisfactory. So by putting all this together, we came up with this system as shown in the figure. As you can see, there are a total of 32 DSLR cameras. They're all time synchronized, so that a press of a shutter fires up all the cameras within 10 millisecond latency gap. We have a very stable power supply so that all the cameras can be turned on and off by using this one switch. And then what's not shown in the figure, in the image, is actually a computer that drives all this camera system. So we have a computer system that has NVIDIA 1080 Ti GPUs. We actually have 2 GPUs mounted on the computer because in the future we're going to do a lot of image processing and computational geometry calculations. So it's actually beneficial to have multiple GPUs. So that's basically how the setup looked like, and that was the scope of this Driver360 project. So, in summary, computerized characters and avatars play important roles in simulation, and then also in the meantime, having a realistic 3D graphical model helps creating synthetic data sets for computer vision. Especially, we are interested in vehicle monitoring type of systems. So the technique called photogrammetry or videogrammetry permits rapid acquisition of higher definition of avatars through the reconstruction of 3D information from multi-perspective images. And then the goal of and the scope of this SaferSim project was to build that camera system, the hardware setup that can be added onto MiniSim simulator to facilitate image acquisition process for us. So the future direction that we're going by using this system would be to, first of all, build a pipeline for data collection. So what you're seeing on the left-hand side is actually a 3D reconstructed model of a driver. So this is actually one of my undergraduate students who worked for the development of this Driver360 system. So this is basically what we can produce, and then we want to be able to have a nicely defined pipeline for data collection. So right now we have all the hardware set up ready. Now there are a couple of things on the software side to facilitate the data acquisition. So right now, each of the cameras are, connected to a computer through USB connection. And then each time we download the video data, we actually have to visit all the cameras by manually going into the folder and then copy and paste the video files. Instead, what we are currently working on is to develop this nice little script which visit all the cameras that are connected through the USB and then download all of the new videos automatically, such that we don't have to manually visit all those 32 cameras individually. There are many other things that we can do to improve the quality of the 3D model. One idea that we're exploring right now is to use those convolutional neural networks, deep learning algorithms, to pre-process the images such that we can remove the background really nicely and then recognize the body joint locations and the facial expressions and things like that before to doing the 3D reconstruction, such that when we get to do the 3D reconstruction, we have a lot richer information than the raw pixels. Another idea is to, when we do the post-processing, we could actually automate the process of skeleton rigging and then mesh reparametrization and all of that, which are necessary steps toward integrating a raw scan data into an actual 3D graphical environment. So we have some projects going on in parallel in terms of developing an automatic computational geometry algorithms for post-processing. And eventually our goal is to build an open public data repository where all of the data produced from this system is gathered and open to the public, so that researchers out there can download the data and then use this data. And then our hope right now is, so far it's a blue sky discussion, but our hope right now is whenever we do driving studies using MiniSim, instead of having one or two cameras recording the driver, if we have a 3D view of the driver, we might be able to discover some new knowledge that were not seen from the previous study because of the limitations of the imaging devices. Not to mention, the other purposes, which is to create a realistic 3D avatars and then create a database for training computer vision models. So all of these data will become publicly available eventually once we have this image acquisition pipeline defined nicely on the system. So that's all I got for today. If you have any questions, I'll be happy to answer that. If you want to follow up, what you see on the bottom is the website, and then my email address is available over there. So feel free to send me an email if you have any question or request. I'll be happy to answer those. Thank you very much.
Thank you, Steve. I am gonna mute you while I'm talking because I think we are getting some sort of feedback there. We did get a question come in during the presentation, which I'm not sure is, I don't know if it's under the scope of this project, but if you have any ideas or any thoughts on it, that would be interesting. So we had a question come in, how does body type affect your research? That is body fat, etc., any other body type information like that, is that relevant to the crash? And let me unmute you quick to see. There we go.
So, yeah, that's an excellent question. So, apparently, we want to understand the effect of different body types in a lot of different scenarios. So, the crash simulation could be, another thing that this type of research can facilitate. So, right now, those crash dummies are modeled, as rigid body, and then unfortunately, the real people are not rigid bodies. So the crash dummy is, at most crash dummy. You cannot really derive any, meaningful knowledge that when it comes to the actual population of the people. So, uh, even though the scope right now is for the development of the avatar itself, in the future, yeah, we definitely want to use this, more diversified avatars for, designing, better and safer, vehicle systems. And then, yeah, I guess, the crash simulation, that takes into account the body fat and different body types. I think those are excellent questions that we can answer in the future by using this avatars captured from our system.